No data, no problem. Giving nuclear inspectors better tools without revealing state secrets. 20 years ago this September, 2 planes flew into the Twin Towers in New York City. Almost 8 years ago, 2 homemade bombs were detonated at the finish line of the Boston Marathon, only a bit more than 26.2 miles away from my own front door. Both of these events were horrible acts of terrorism, but we're tremendously fortunate that neither involved a nuclear explosive. In fact, we've never had an act of nuclear terrorism, and a big part of that is due to international cooperation to safeguard the incredibly potent nuclear materials at the heart of these weapons. But even though a nuclear terror catastrophe has never occurred, we can't stop being vigilant. The role of inspectors from the International Atomic Energy Agency, the IAEA, is always to stay ahead of those looking to divert and misuse nuclear material, for whatever sinister purposes they can come up with, not just nukes, but also things like dirty bombs. Most of the time, this is straightforward. Treaties and agreements with the IAEA dictate who, what, where, and when the IAEA can inspect. States that do not comply with these rules risk running afoul of international law, like the Treaty on the Non-Proliferation of Nuclear Weapons. All but 4 countries have signed the treaty, and on this map they're shaded in red. Signatories possessing nuclear weapons are shaded in blue, and those without them are shaded in green. For better or worse, as sophisticated data analytics become ubiquitous, it's anticipated that states will also be increasingly reluctant to share anything more than the minimum amount of information that's required under their safeguards agreement in the IAEA. This is not generally because they intend to act illegally or make a nuclear weapon, but rather because they wish to protect proprietary business advantages or sensitive state information. Still, while these protective stances aren't necessarily a bad thing when it comes to individual national security, for the vast majority of states at least, they may pose an impediment to the IAEA detecting a diversion somewhere, and that could lead to a catastrophe. So can we devise a system that appeases both parties? One that lets states retain high levels of privacy, while the IAEA inspectors can be notified about real deviations from expected practice? Well, we're looking at the intersection of privacy and security, where the cryptographic subfield of secure multiparty computation becomes applicable. If you aren't familiar with the field, secure multiparty computation, or MPC for short, allows 2 or more parties to jointly compute some function of all their inputs together, while none of the parties learns anything about the input of any other party beyond what's implied by the result. It sounds a bit like magic, but I assure you it's computationally sound. The idea of MPC has its roots in the late 1970s and early 1980s, and I'll largely be focusing here on one class of MPC algorithms called garbled circuits, credited to the cryptographer Andrew Yao in the 1980s. Yao presented what he called the millionaire's problem. 2 millionaires go out to dinner, agreeing that the richer one covers the meal. Neither wishes to disclose their true net worth, so they devise an algorithm to indicate who's paying, and nothing else. There was more formulation in mathematical theory that was developed through the 1990s, and by the early 2000s, software was being written to actually implement these algorithms. As computing power has grown, the abilities of software implementations have grown with them, with MPC really only entering the scene as a practical technology in the past decade. A couple examples are privacy-preserving cryptocurrencies like Zcash, or an anonymous study on gender wage gaps by Boston University in 2015. COVID-19 contact tracing has also recently spiked in interest in these algorithms too. And so with all this development, we decided to try applying MPC to our own safeguards problem. At the most basic level, we were asking the following questions. What can we actually do with MPC? Which specific safeguards problems would lend themselves to it? What types of data could we analyze? And why isn't this already being deployed? Let's start with this first question. The key insight about Yao's garbled circuits, and subsequent evolutions of them, is that they can handle literally any calculation that might be performed by multiple parties. If you can program a computer to do it, you can build a circuit to do it too. And I'll come back to this in a bit. As far as what data we could use, well, we decided that an interesting exercise would be using MPC to analyze the output of detectors like those relied on by IAEA inspectors. Since every radioactive isotope, think flavor of an element, produces a unique radiation signature, measuring these emitted radioactive particles can tell an inspector exactly how much nuclear material and what types are in a location. This plot of the spectra produced by uranium ore serves as a good illustration. You can see the distinct spectral peaks, each one where the detector measured many radioactive particles of the same energy. And while none of these peaks actually corresponds to the radiation from uranium itself, they do come from a cocktail of radioactive particles that's really only produced in this observed ratio by uranium ore. Taking this idea further, perhaps if we could watch the output of a detector over time, we could flag measurements with radioactive signatures for nuclear materials that are proliferation risks. This is what the IAEA inspectors and data analysts already do, but with MPC we could do it obliviously. We'd learn nothing else about the material compositions that are picked up by the detector. Which brings us back to the third question. Why hasn't anyone done this yet? Well, on one hand, the technical requirements of MPC mean that only very recently have off-the-shelf computer systems been able to handle privacy-preserving computations of what I would truly consider data analytics. Additionally, the IAEA is necessarily incredibly risk-averse. You can't ride the cutting edge without taking risks. And when it comes to nuclear security, losing bets are not acceptable. The IAEA has to ensure that every technology put into practice is guaranteed to work. Oftentimes, this also means deployed technologies are customized to be extra secure and extra resilient. The IAEA's technology tends to be tried and true, not latest and greatest. And finally, nuclear safeguards is a small field on a constrained budget. The pool of expertise is pretty limited, and unlike a lot of tech fields, nuclear safeguards isn't a moneymaker. That means that the technical overlap between nuclear fields and the latest in cryptography is just pretty small. Now, before I show you what we accomplished, I want to take a few minutes to explain how MPC actually works. It's super cool, but I told you it wasn't magic, and so I'm going to have to back that up. You may have learned at some point that any calculation your computer can do can be performed using a digital logic circuit. This circuit here shows a simple calculation. Is bit A, the circuit's input wire on the top left, greater than, less than, or equal to bit B, the input wire on the bottom left? By adding gates, the circuit can be scaled up to do almost anything. Real numbers are reduced to binary, and every addition, subtraction, multiplication, division, square root, modulus, exponential, you name it, is represented using a complex system of logic gates. Not, and, or, and the like. Garbled circuits build on this foundation. Let's look at the two-party case. To keep the focus on safeguards, we'll say one party is a nuclear facility, and the other is the IAEA. Our two parties agree on a function to compute. For simplicity, let's imagine a function that tells us if the two parties have picked different numbers from just the small set of integers 0 through 3. Since our circuit will work in binary, we convert our integer possibilities to base 2 and get 0, 0, 0, 1, 1, 0, and 1, 1. We see that we have 2-bit inputs for each party. Each party has 2 input wires to the circuit, and the party's integers are only the same if each bit in each input is the same. The gate that gives a 1 only when the bits are identical is the XNOR gate. You can see that on this truth table here. We have 2 of these XNOR gates, 1 for each pair of bits. Then, since both pairs of bits have to be the same, an AND gate gives us an output value of 1 only when both of the XNOR gates confirm a match. Now, this is all relatively straightforward, and we can see all the bits clear as day. However, we need the circuit to be garbled. Let's imagine that the facility goes through this circuit and replaces the 2 values on each wire with 2 random strings that only they know. Starting with the first XNOR gate, we replace the 0 and 1 on the first input wire, then 0 and 1 on the second input wire, and finally 0 and 1 on the output wire. We repeat this process for the second XNOR gate, and finally, one last time for the AND gate. After the labels are added, we can still see the pattern from before, but that's the only thing that tells us whether a label corresponds to a 0 or a 1. Next, the facility uses the input wire labels for each gate to symmetrically encrypt the gate's output wire label. We start in the first table, encrypting the first row, then the second, third, and fourth. The process is the same in the other 2. This produces 4 encrypted tokens for each gate, 1 for each row in the truth table. If the facility were to hand you 1 token for each of the input wires to a gate, you could only successfully decrypt 1 of the 4 outputs. And the only thing indicating now which encrypted token belongs to which row is the fact that they haven't moved from where they started. So let's change that. Now, remember, up until this point, every step we've seen was performed by one party. the facility. The facility knows all the labels and what values they represent, and so they can give the labels matching their own input values to the IAEA. Since the other party hasn't seen any of this yet, they don't know which random label matches which wire value. That label is just a random string to them. Now, the IAEA needs to get the labels for its own input wire values. But this presents a dilemma. It can't directly ask the facility for the label corresponding to its bit choice, because then the facility knows that the IAEA's input is whichever one it asked for. Likewise, the IAEA can't be shown both labels and the matching values, because then it will be able to decrypt more than just one of the encrypted rows in the truth table. We solved this using something called oblivious transfer. We'll treat it as a black box, where the generator party can put both labels into the box, and through an interactive process of encryption and decryption, the IAEA gets only one label of its choice. I'll reiterate that. The IAEA learns only one label, and the generator learns nothing. After executing oblivious transfer, the IAEA has all the labels it needs, labels matching its own known values, and labels matching the facility's unknown values. The IAEA can start walking through the circuit, successfully decrypting only one token for each gate. This decrypted token reveals the label on that gate's output wire, which can then be used as a decryption key for the next gate. Again, this process repeats for each gate in the circuit. Finally, once the IAEA has the computed label on the circuit's output wire, it can share that label back to the facility so that the computation result becomes public. So now that we've covered the fundamental cryptography, let's get back to real implementations. I told you before that we wanted to be able to identify anomalies in radiation spectra, effectively demonstrating that MPC worked on safeguards data. At the same time, knowing our audience of safeguards inspectors and data analysts, we recognized that if this was ever going to be more than just a fun idea, we needed to be able to do it in a way that was clear and convincing, especially to folks at the IAEA who might not be at the forefront of cryptographic research. We surveyed available MPC software frameworks and found a pretty wide range of options available, which is great. These were codes that satisfied our obvious criteria of being able to perform calculations correctly while keeping data private, but all of them presented other challenges. Some were too limited in their ability to handle a challenge of this scope. Some are no longer maintained. Others are commercial, and so while potentially great for a contract down the line, they're not so great for a highly tailored demo with full transparency. But most often, the codes were state-of-the-art research codes designed to showcase the latest development in the field, and were just too sophisticated for building a demo aimed at a budget-constrained inspector with a relatively limited base of expertise. For perspective on this last point, there was a fantastic systemization of knowledge study published in 2019 by researchers at the University of Pennsylvania, surveying a selection of MPC frameworks and related tools. It estimated that learning, building, and testing their selection took 750 person-hours, and even then, they didn't always succeed. That's a computer science PhD candidate working for a month straight. No breaks, no weekends, no sleeping. And so, we built a prototype of our own, a Python package called CipherCircuit. Now, I confess, I'm not a cryptographer, just a nuclear engineer with a passion for reproducible computing. Our prototype evaluates circuits successfully and securely, and while it's admittedly slow, it is highly accessible. Here's a quick snapshot showing how the whole process we just walked through can be encapsulated in just a few lines of Python. The package is designed to be used by anyone who understands the fundamentals of garbled circuits, installed without any headaches, and inspected thoroughly at every step of the circuit evaluation process. But finally, after development, the time came to begin testing garbled circuits on real-world time series anomaly detection datasets. Now, the radiation spectra that we were looking at before tend to be large sets of data. At each point in time, one may monitor hundreds or thousands of channels, each giving a count of how many radioactive particles are measured in some energy range, as you saw earlier. We started smaller, looking to find a univariate time series that we could analyze first as a test. And we settled on something outside the safeguards realm, but which I hope is easily relatable to you all in the audience: an electrocardiogram signal, a heartbeat. Here I've shown a sample of heartbeat data sourced from the Beth Israel Deaconess Congestive Heart Failure database. It's pretty obvious just by looking at it to see where the anomaly is. But for privacy-preserving computation, we can't look at it. Instead, we coded up a garbled circuit to analyze the cardiogram. One party inputs their cardiogram data, the other party inputs parameters of the anomaly detection algorithm. And the result? The garbled circuit identified the exact location of the anomaly, but never revealed the actual cardiogram heartbeat. And so with this successful result, we've pushed on to something far more relevant to nuclear safeguards, using a selection of data that was generously shared by a team at Oak Ridge National Lab, working on the Modeling Urban Scenarios and Experiments Project, or MUSE for short. We began applying garbled circuits to time series of radiation spectra. During February 2019, the MUSE team collected radiation data from along a stretch of road between a research reactor and another facility inside the lab. We knew that at some point during the month, a metal drum containing a mixture that included a specific isotope of protactinium, that's elemental symbol Pa, and it has 233 protons and neutrons, was moved past a roadside detector. Now, this protactinium isotope decays fairly quickly into an isotope of uranium that could be used to build a nuclear weapon. That uranium isotope is exceedingly rare in the natural environment, so creating other materials that decay into it is the only viable means of production. So watching for the radiation signature of the short-lived protactinium is comparable to what an inspector might be interested in. And so began our blind treasure hunt. Could we identify the exact date and time when the protactinium passed the detector, without ever actually looking at the detector's output? I'll show you. Here's an animation of just a few minutes of data collection on one morning in late February. The animation is sped up, so you won't have to stay still quite that long. On the left is the view that a facility might have. The plot gives the radiation spectra that was actually measured, in this case the MUSE data. You can hopefully see the jitter at the bottom of the plot. That's background radiation. It's everywhere, all the time, including around you right now. It's low enough that it has almost no impact on your life, but the detectors see it, and so our algorithms must filter it out. Then, on the right, is the view an inspector might have, using a garbled circuit. At the top is a rough example of the radiation signature of the protactinium. You can see a large peak at around 300 kiloelectron-volts, keV, and a smaller peak at around 400 keV. That's what we've built the garbled circuit to look for. The lower energy peak is less likely to show up reliably on the detector, so we're ignoring that one. At the bottom is an indicator of whether the data input by the facility shows hints of protactinium. Green is good to go, and red is an anomaly. Here, detected at 9:19 a.m. It's a success. Now, as I mentioned before, our package is fairly slow, and so our goal is to speed this up to something approaching real time. After that, ideally we move to implement the package as a language in and of itself, akin to most of the existing frameworks available today where circuits can be built as computer code, not wire by wire, gate by gate like I showed before. That gets tedious. There are also some other obvious challenges that lay in front of us. How will we deal with malicious adversaries? These are participants who might try to subvert the calculation by not following the rules of garbled circuits. And fortunately, this is a problem that's actually generally been solved in the literature, and so we just need to build it into our own methods. Perhaps more importantly, can we prevent parties from spoofing their input data? Garbage in, garbage out, as the saying goes, but adding techniques like commitment schemes to the procedure could ensure that when a party enters data, it becomes immutable, enabling the inspector to return and verify its authenticity at some point in the future if it's deemed necessary. Despite these challenges, I believe that this technology is needed now more than ever. As international relationships are becoming increasingly strained, the ability to use trustless, privacy-preserving systems may allow us to maintain relationships and international cooperation around nuclear safeguards. Hopefully, they even present the opportunity to rebuild trust between nations that may not currently see eye to eye. And so, for all you nuclear inspectors in the audience, let's consider where MPC might fit into the IAEA's future operations, shall we? And for anyone who's left, I believe that MPC could have applications in almost every aspect of modern life. And so I challenge you to think about where and when you might desire privacy-preserving computation in your own daily routine. And then I hope you'll push for MPC to go mainstream.